For lesson 5, we're going to actually split this into 2 parts. And so today, while we're focusing on the zeros of polynomial functions in both sections, we're going to look at things pretty straightforwardly today. This will be maybe the easier version of lesson 3.5, and the part B is going to revolve around the quadratic formula after we've done some factoring, after we've done some division, and we'll have to do just a little extra work. We're here today, hopefully the answers just call out to us from the work that we do. So our goal today is to model and solve problems using the zeros of polynomial functions, and we have to understand again and remind ourselves of what the zeros are. So the zeros are essentially the x-intercepts, right? The values of x that make the output 0. So the x-intercepts have an x comma y, and you know what the x is, you know that y is 0, so the x value is the 0 of the polynomial function. And one of the things that we want to make sure is that we have this output equal to 0. So there's some reminders here that are helpful to be aware of. If we know what the zeros are, then we know what the factors are, we know what the zeros are. All of that is related to one another. If we know what value of a makes y equals 0, or what value of x, we know that x minus a is a factor of that function. And so all of these are interrelated. If we can find the x-intercepts, then we know the zeros. If we can find a factor such that the remainder is 0, then we have the 0. And so all of that is really tied well together here. We're kind of seeing it all come to fruition. But that means that we have to be up on our game for all the other parts of this unit. So here we have 2 functions. One is factored, one is not factored. So just a reminder, when things are factored, that is awesome. This means that we want to show when does y equal 0? When does 0 equal x minus 7 times x minus 5 times 2x plus 3? In order to attempt to address this when it's already factored, the work is basically done for us. So I'm going to show you that work. If this times this equals 0, then that means that 0 is equal to x minus 7, or 7 equals x. It means that 0 is equal to this factor, x minus 5, so 5 is equal to x. It means that 0 is equal to 2x plus 3, so it means that negative 3 is equal to 2x, and negative 3 halves, or negative 1.5, is equal to x. These 3 values of x are the zeros of this polynomial function. Now I know that that's not multiplied out, that's good news for us. It means that we have less work to do. Now, for some of these, you probably are going to be tempted to skip this step, that 0 equals x minus 7, that 0 equals x minus 5. Can I just write 5? But here, you're going to need to show that work, all right? I strongly advise that you write this step so you can get these answers. Over on this one, this is not factored yet, so we can't just answer this question. What we want to be able to do is factor this polynomial to make sure that we have x squared minus x minus 12, and then be able to factor the quadratic part here. So we have 3x times x minus 4 and x plus 3. Of course, doing our algebra 1 factoring of that quadratic. Take as much time or space as you need to on this. If you're doing some other gimmick, great. If you're doing the AC method, awesome. But make sure that you can factor that quadratic, hopefully pretty quickly. If these are our factors, then we want to set each of those equal to 0. Right? We want to find out what happens, what values of x makes y equal 0. So these values of x are the zeros of the function. When does 0 equal 3x? Well, that happens when 0 is equal to x. When does 0 equal x minus 4? Well, that happens when x is equal to 4. When does 0 equal x plus 3? Well, that happens when x is equal to negative 3. So these are the zeros for this function. All right, we can also find those zeros by graphing, and we'll talk through that here in just a little bit, because we're going to talk about multiplicity. And multiplicity has a sort of a definition that we've already explored in previous conversations last semester, but for those of us that maybe don't remember or weren't engaged with this as much last semester, multiplicity is when a 0 is repeated. We usually refer to that as multiplicity, but really it's just the number of times that 0's associated factor occurs in the factored form of the function. So I know that sounds really crazy. Basically, here's what this means. This means that x minus 1 happens twice, So that means that x minus 1, or in this case x equals 1 is a 0, has a multiplicity of 2 because it happens 2 times. X plus 2, that factor occurs 1 time, so we would say x equals negative 2 has a multiplicity of 1. Now, typically, if there's multiplicity greater than 1, we write it. If there's not multiplicity greater than 1, we just write the 0 without stating that it has multiplicity. If it has multiplicity, it's expected that we write that it does have a multiplicity of 2. Another way to write that would be that x is equal to 1 and negative 2. But if we're supposed to state, if we're directed to state that there's multiplicity, then we need to state that there's multiplicity of 2. I'm just abbreviating the word multiplicity there. I hope that that's okay. But looking at this from the standpoint of multiple zeros, and again, we kind of discussed what that looks like when we graph it. What's the graph going to look like at x equals positive 1 versus what is it going to look like at x equals negative 2. What we want to do first is just make sure that we can understand these ideas of multiplicity. So in this case, we have y is equal to x times x squared minus 4x plus 4. And when we finish factoring that, we find out that this is x minus 2 and x minus 2, or a good way to write that would be x minus 2 squared. So again, this is x, and then x minus 2 and x minus 2. So since this is a repeated factor, we know that if I'm solving this equation, trying to find the zeros, I know that x equals 0 because of this factor, and I know that x minus 2, is equal to 0 twice. I do not want to solve this equation twice, and so I'm not going to write it twice. Instead, I'm going to write x equals 2, but with a multiplicity of 2. This degree, this is happening twice, and so we're going to give this as a 0 and that as a 0, x equals 0. Over here, we can see that if this is already factored, congratulations, that's awesome, it saves us this hassle. We can tell that there are going to be, oh my gosh, this is such a big polynomial. Who cares? What we know is that 2x minus 3 is equal to 0. And that means that x is going to equal 3 halves, but with a multiplicity of 3. All right? With a multiplicity of 3. Over here, this is x plus 5 equals 0, so x equals negative 5 with a multiplicity of how many? With a multiplicity of 7. And here we have also, let's circle these. Here we also have 3x plus 1 equals 0, when 3x equals negative 1, or x is negative 1/3, and this has a multiplicity of 1. Now, I'm not a big fan of writing multiplicity of 1. Notice how I didn't write that this has multiplicity of 1, because I don't usually care to write it, and you are generally not going to care to write it. And so I am actually going to be generally okay with you not stating that there's multiplicity of 1, only stating it if there's more than one multiple 0 at that location on the graph. All right? On these, I would like for, I'm going to do this one, and I'm going to ask you to do that one. And there's a little trick happening here with this x equals 0. You kind of see what that looks like in factored form on the last one, but this is going to be u try. This is going to be a u try. But over here, for example, 3, writing functions given the zeros. We've got y is equal to x minus a, and x minus this factor, and x minus that factor. So the factored form here is going to be x minus negative 4, x minus negative 2, and x minus positive 1. So this is the factored form, and we're going to do this in kind of 2 different ways. One is first making sure that we get this. Before we move on and actually multiply that out like we did last semester in lesson 3.2b, or lesson 3.2, what I want to make sure that we do is that we can write the factored form. X equals negative 4 only if x plus 4 is a factor. X equals negative 2 only if x plus 2 is a factor. X equals 1 only if x minus 1 is a factor. So we are going to then expand this out. Once we have this, great, we have to do that well. We are going to factor these out, FOIL these out, multiply these out using double distribution, and in this case triple distribution to multiply x squared times x to get x cubed. X squared times negative 1 is negative 1x squared. 6x and x is 6x squared. 6x and negative 1 is negative 6x. 8 times x and 8 times negative 1. We've got like terms to combine. So this is the standard form of the polynomial function that has zeros at these locations, all right, without any multiplicity. What I want for you to do is I want you to write in the factored form, and then I want you to try to multiply it out like we did last unit. So you do this one, write down y equals and then all of your factors, and then multiply that through. So I want for you to try that one. I will do this one, and then I'm also going to do letter D. Sorry that there's a lot of examples on here. I know it makes the video go a little bit longer, but again, the goal here, pause the video if you need to work on that last page to make sure you get that done. Again, if x is equal to negative 3/4, that means that 4 times x is equal to negative 3, and 4x plus 3 is equal to 0. This is our factor, 4x plus 3. So we'll have y equals 4x plus 3, and we'll have x minus that a value, x minus 5. So if again we have this as the factored form, we can do double distribution to get 4x squared minus 20x's plus 3x's minus 15. And so we have y is equal to 4x squared minus 17x's, minus 15. On this one, it says x equals 1/5. So I'm going to multiply 5 times x equals 1, and then subtract 1 to make sure that we have this factor. But this factor is multiplicity of 3, so that means that we have y equals that factor cubed. This would be the factored form. We want to be able to multiply this out all the way. And we can do that because we did it last semester and we were very successful with that. When I multiply this first pair together, I get 25x squared minus 10x plus 1. And then I need to multiply all of those by 5x and by 1. So I'm going to multiply it by 5x. Here I'm going to multiply by 1. Here I'm going to multiply by 5x. And then I'm going to multiply by negative 1. Multiply by 5x. Multiply by negative 1. Combine my like terms, my squares and my linears. Y is equal to 125x cubed minus 75x squared plus 15x is minus 1. Let me know if I made any mistakes in there. All right, so here we've written the factored form, and that factored form is huge. That factored form is huge. And then this is our standard form. Both of them are valuable. Both of them have their places in our work. We can't get this if we don't know that. So let's focus on this and then be able to do that work as requested or as needed. Hopefully this is going well. If I'm going too quickly, be sure to ask questions on this. Here, extending our understanding of multiplicity, I wanted to point out a couple of fun facts. When we are talking about zeros, again, zeros are where the graph crosses the x-axis, where it has an output y equals 0. And so we can see the zeros in these locations. But what I want to highlight here is, and I don't know how well you can see it on your screen there, so you might have to make your window bigger so you can see this very well. But here we have a 0 at negative 2 and a 0 at positive 1. And so if I have a 0 at positive 1, it means x minus 1 is a factor. If I've got a 0 at x equals negative 2, x plus 2 is a factor. Here, this kind of touches and bounces off. Here it crosses, so I know that x minus negative 2 or x plus 2 is a factor. But here at x equals positive 1, x minus 1, there is a multiplicity there. So when it touches and bounces off, that is usually an even number of multiplicity. All right, I know that sounds awkward. When it crosses, it just happens once, right? That's once. So the multiplicity is 1 on those factors. Here, it touches and bounces off, and so we know that there is multiplicity. Now this multiplicity is maybe a little confusing. Here, obviously, this factor comes just straight through, but this one, it like comes up and it touches and then it continues on. So it's kind of like awkward right there because our slope is 0, right? It's kind of like a local min and a local max kind of at the same, and then it kind of continues on. It's very awkward Because what's happening there is we have an odd multiplicity at x equals positive 1. So this is one of these things that we want to make sure that we're just attentive to and watching out for. These fun facts, please kind of keep straight in your thinking. Write that down in your notes. If your multiplicity is odd, then it will cross the axis. If your multiplicity is even, it will bounce off the axis. It'll touch it and it'll kind of move on. So here it touches and it moves on. Here it touches and it bounces back off. All right? Here it crosses. Here it's an odd multiplicity and it touches and then it continues on. All right? So that's this one's kind of awkward to visualize. This might be a difficult concept, but I want for us to be able to describe what we're seeing in our graphs. So here is where we're asking you to do this. Here, again, I want you to try to do this. Example 4b. All right, you're going to try to do that one. But for this, we're going to say that there are zeros. I'm going to use a different color here. There are zeros at x equals 0. Multiplicity is 3. Zeros at x equals 5. Multiplicity 1. And a 0 at x equals -2, multiplicity 5. And so we found the zeros, we've got the multiplicity for each one, and then we're going to talk about whether it crosses or just touches. Since these are all odd, it crosses the x-axis. All right, crosses the x-axis. Crosses the x-axis at those values of x. All right, so we can kind of predict maybe a little bit about what these are going to look like. So here's -2, boop. Here's 0, and here's 1, 2, 3, 4, 5. Not to scale, but there's 5. All right, so what's going to happen here is that this is obviously positive, and it is a total of 9, so it's an odd degree. All right, it's a total of an odd degree polynomial. So what this is going to look like is it's going to come up through here. It's going to come back down, but it's going to do like that little wobble there, right? It's going to come down and go like bloop. And then it's going to come back up this way, all right? Oops, wait, this is going to be awkward. Let me start that over. We're coming up and we kind of get a little wiggly. We're coming down and we get a little wiggly. And then here we're just coming straight through. It does cross, but it gets a little awkward right in here where it kind of flattens out. It's a little awkward right in there, but then where it looks like it's flattening out and then it goes on. Over here, I want you to try to do, and I want you to try to sketch. Now, if you want to cheat on the sketching, you can just graph it, right? That will do the trick. But that will probably get you a visual of what that is supposed to look like for us in our graphing. So this is hard, right? This is hard thinking about what we're doing. Maybe finding our zeros, stating the multiplicity, that should be the easy part. I know it's new, but that should be the easy part. But thinking about it, what it's going to look like before we type it in our graph or before we do all that work, we should be able to kind of visualize what that graph might look like. So hopefully you have a good understanding of how to model and solve some issues dealing with the zeros of polynomial functions.